So the good news is that we only have 3 more integrals to learn. After these 3, there are no new integrals for us to have to memorize this year anyway. There are no new derivatives. Like this is the end of everything. The bad news is that there they are. They are challenging. They are complicated, and they do deal with inverse trig, which is challenging. But they are related to the stuff that we did yesterday. And if you've written these down, I'd recommend you compare this to what we looked at yesterday. Right? What we saw yesterday was that the derivative of arcsine was 1 over the square root of 1 minus x squared. The derivative of arctangent was 1 over 1 plus x squared. The derivative of arcsecant x was 1 over the absolute value of x times the square root of x squared minus 1. You may not have those memorized yet. You really should get on that. But the idea is these are related to the things that we did yesterday, and then they're not entirely new. I want to make a couple of comments about these before we jump right into examples, because the reality is we just need to practice these things. We just need to get the hang of it. And the comment that I need to make, and this is very, very crucial, is that in all of these cases, a is a constant, and x is a variable. Right? So the thing you need to recognize is, because the hard part about these problems is knowing when you're supposed to use these things and when you're supposed to do some kind of a U-substitution. So the deal is, when you have a square root and it's the constant minus the variable squared, that's going to be arcsine. When there's a square root and it's the variable minus a constant squared, the other way around, it's going to be arcsecant. And when you have not a square root and the two squared things are added to one another, it's going to be arctangent. That's going to be a little bit cryptic right now, but as I go through examples, I hope to make that more clear. So I'm just going to get right into the first example. So the first one of these that I want to tackle is the antiderivative of 1 over the square root of 25 minus x squared dx. And so again, the struggle in these problems is figuring out, like, which one of the rules is it? Is it just a U-substitution? What is this about? Because in some sense, you guys have dealt with similar problems. We've dealt with things before that are like this. Oops, and I didn't mean to put a 1 on the top. I meant to put an x on the top. If we had been doing this problem over here, you would just do a U-substitution. You would do 25 minus x squared, and the reason we know that is that the derivative of 25 minus x squared is negative 2x, and that's related to the x that's on top. In this one, there is no x that's on the top. If you tried to do that U-substitution, it would not have worked. In this case, we need to recognize, hey, wait a minute, on the bottom there's a constant squared, there's an x squared, they're subtracted, and they're inside of a square root. This is like a perfect setup for the arcsine rule that we just learned. Right? So the thing that I recommend everybody does is actually take a step to rewrite this. Actually write it as 5 squared minus x squared dx. Doing that, I think, makes it really clear. You can see, oh, this is the a squared, this is the x squared, and so because of that, I can just follow the rule for arcsine. The rule was that it's going to be arcsine of x, that's the variable part, x over a, that's the constant part, x over 5 plus c. And that's your answer. Okay? Let's go on and look at another one. So my next example, the integral of 7 over 100 plus x squared dx. So here again, we're looking at a problem that previously might have been a U-substitution problem. If there had been an x on the top of here, this bottom thing is the u would have been perfect, but there isn't an x, so we start to look at it a different way. We start to see it that this is a constant squared, it's 10 squared. This is a variable squared, it's x squared. There's no square root, they're added together. This feels like arctangent. Look earlier at your notes, you'll notice this looks really similar. So we start by writing it differently. I'm going to pull the constant of 7 out. 7 times the integral of 1 over 10 squared plus x squared dx. And again, at this point, that should look just like the arctangent formula. Right? So we remember that arctan starts with 1 over a. A is our constant, so 1 over 10 times arctangent of x, that's our variable part, x over a, which is our constant part, 10 plus c. And the last thing I can do to make it prettier is to do this. And that's our answer. Okay. I have one more basic example before I go into to some more complicated examples. So here's that last sort of basic example. The integral of 10 over x times the square root of x squared minus 4 dx. So, if you're doing this at home, take a minute and pause the video, try that one on your own, see if you can make that connection. So here we go. I'm going to pull out that 10. I'll have the integral of 1 over x times the square root of x squared minus, and some of you at this point may even be comfortable just saying, I'm going to write that 4 as 2 squared. Because when we do that, we recognize that this looks like arcsecant. It has the x on the outside like it's supposed to. It has the same x squared on the inside. It has this 2 squared. Like, we have all the pieces that we need for that. So then we just remember that the arcsecant formula is, we've got the 10 from before, 1 over a, my value of a is 2, times arcsecant of, now the numerator of this is supposed to be the absolute value of x. Well, x is still our variable term, it's x, over a, which was 2, plus c. Last thing I can do is I can pretty up the front of that. This is 5 arcsecant, absolute value of x over 2, all plus c. Okay, so those are my 3 basic examples. I've got 3 that are a little bit more complicated, so we'll go through those. So if you've had an easy time with these, great. What I'm going to introduce now is the fact that U-substitution can happen with these, and it can get complicated. Not too bad, but we need to take a look at it. So this next example that's slightly more complicated is for us to do the integral of 1 over 9 plus 4x squared dx. So does this look like which of the 3 rules does this look like to you? And if you need to, pause the video, look at the original 3, see what this looks like to you. This should look like arctangent, right? Because it looks like there's a constant squared and there's a variable squared going on. There's a 4 there, so we'll have to deal with that, but the idea is that's a variable squared. So I'm going to start by rewriting this, and I want to really write it in the form 1 over something squared plus something else squared dx. So the 9 I could write as 3 squared. The 4x squared I could write as 2x squared. And the place where people make the mistake is they go, oh yay, it's arctangent. I can just write, and I'll write it in red so that we understand that it's wrong. They write, oh, it's 1 over a times the arctangent of variable over a. And that's not quite right. And the reason it's not quite right, and you've heard this language before, the thing inside of this is not just x. We don't know how to do the integral of 1 over 3 squared plus 2x squared. We know how to do 1 over 3 squared plus x squared. This problem is basically calling for a U-substitution. I need to make my U the thing, and I'm using quotes with my fingers right now, the thing that's supposed to be just x. The thing that's supposed to be just x is 2x. So I'm going to go U is 2x, du is 1 over 2, I'm sorry, 1 over 2. I got a step ahead of myself. Du is 2 dx, so 1/2 du is dx. Now I can bring these things back to my problem. I'll have the integral of 1 over 3 squared plus u squared times 1/2 du. I'm going to put the du here and pull the 1/2 out front because we've gotten used to that. Now this looks exactly like arctangent. Now I can say that this is 1/2 times, now the integral for arctangent is supposed to be 1 over a arctan of quote-unquote x, which in this case is u, over a plus c. And then my last step is plugging back in that u value. So I get 1/6 arctan of 2x over 3 plus c, and that's our answer. Note that that's different from the red wrong answer that I got up here, because we were missing this 1/2 factor that came from the U-substitution. So, like I said, the U-substitutions can be a little weird, but there we go. I think I just have one. I had 2 more examples, but I'm gonna cut one of them out so I can keep this one a little shorter, and I'll do some more examples in a second video. Because really all we need here are examples. We just need more and more practice with this. So we'll do the integral of 1 over x times the square root of 4x squared minus 1 dx. Right? So again, pause the video, figure out which one this looks like. Hopefully you recognize that this looks like arcsecant. It's got an x, it's got a square root, then inside it has variable squared minus constant squared. This looks pretty good so far. So just like I did before, I'm going to sort of recommend that we really try and write this thing exactly in its other form, right? I'm going to see this as, I can see the 4x as 2x squared, and I can see the 1 as 1 squared. And so now the issue is that the issue is that this thing right here was supposed to just be a variable. It was supposed to just be u. So I'm going to do a u substitution and use u equals 2x. From there, my du is 2 dx. So I get 1/2 du is dx. And now I'm going to take these things and plug them back in. And you're going to see a trick from before. So this is the integral of 1 over, now I've got an x here, and we'll have to deal with that. This will be the square root. And the whole point of this was so that I could say this is u squared minus 1 squared. And then my dx on the end is 1/2 du. Right? Now, I've got a couple of issues. One, there's this 1/2, and we could pull that out front for sure, but the other issue is I've got this x here, and I need to somehow make that go away. What I'm going to do is I'm going to kill 2 birds with 1 stone. If this x here had been a 2x, then I could replace it for a u. So instead of pulling this 1/2 all the way out front, I'm just going to take the 2 and multiply it to the bottom. I'll write this as 1 over 2x times the square root of u squared minus 1 squared du. And now that 2x can be changed into a u. And the question that I have to ask you is that good news? And I think it is, because the reality is this is now in the perfect form for arcsecant. And I actually need us to look back up here. Note, this is not perfect form for arcsecant. I know we normally want an x out here, but now that I've done a u substitution, what I really want out here is a u. Like, I need it to be variable times the square root of variable squared minus 1 squared. I need these 2 variables to be the same. So now that they're the same, I can take that integral. The integral is 1 over a, which is 1, times arcsecant of the absolute value of variable over a plus c. And so to bring this all to completion, we end up with just arcsecant of the absolute value of 2x plus c. And that's our answer. I know this video is a little on the long side, but there are only going to be 2. I'm not going to make a third one tonight. In the second video, I am going to cover some other things, particularly including bounds and just more examples. So make sure you check out that second one after you've recovered from this one. So I'll see you there.